Great. So my name is Laura Supple, and I've been working with Dr. Andy Miller at the University of Maryland, Baltimore County, and our project has been focused on the hydrology and hydraulics of urban floodplains. Urban waterways typically exhibit a particular form of degradation that's been described as the urban stream syndrome. The urban stream syndrome is characterized by high storm flows that erode banks and deepen channels and disconnect the stream from the floodplain. So there are not only ecological consequences from this, but threats to property and infrastructure as well. So two of the main approaches to combat the urban stream syndrome are stormwater mitigation and stream restoration. Stormwater mitigation typically attempts to control the volume and intensity of stormwater runoff at the watershed scale. So an example of this might be a stormwater retention basin. Stream restoration, on the other hand, typically uses direct morphological intervention to improve the stability of channels and slow further degradation. So the purpose of this research project was to gain a better understanding of the relative effectiveness of stream restoration approaches when the upstream watershed conditions remain unchanged. And to address this question, we used novel two-dimensional hydraulic modeling techniques. This study focused on a portion of the Mine Bank Run, which drains an urban area in Baltimore County. You can see another closer image of the study reach here. There have been several restoration projects carried out along much of Mine Bank Run from about 1999 to 2013. So there's been a lot of focus on this area. These restoration projects have been primarily concerned with improving geomorphic stability and reconnecting a deeply incised channel to the floodplain. You can see here some images of the unrestored section on the left and the restored section on the right. You can see the bank slope was decreased a bit and a riprap wall was put in to strengthen the bank. So those are just some examples of the types of restoration techniques that were applied to this stream. So in order to develop this model, 5 hydrographs from flood events captured by a USGS stream gauge at the upstream end of the study reach were used. This particular hydrograph is from the largest event that we looked at from June 1st of 2012, and the peak flow was about 1,300 cubic feet per second. And you can see from this annual maximum flood series for that stream gauge, this flood was about the 4th largest flood in the past 14 years, so it was a significant flood event to look at. Next, a channel floodplain terrain was developed from high-resolution LiDAR and used to construct a terrain elevation model in the newest version of the HECRAS two-dimensional hydraulic modeling software, which was developed by the U.S. Army Corps of Engineers. This terrain data can be directly manipulated to reflect restoration measures. And here you can also see the locations of 3 of the 4 key cross-sections that we monitored between scenarios to assess the response of the system. You can see them highlighted in blue. And you can also see 2 of the Oxbow Wetlands pointed out in the terrain. And those Oxbow Wetlands were an important component of the restoration project. their former portions of the channel that were cut off in the restoration project, but the remnants of the channels have been left to serve as overflow for high storm flows. So one of the things that we looked at was how effective that particular measure was. So here you can see the profile of the original terrain. This is the stream centerline profile. And here you can see the same stream centerline profile of one of the alternative terrains that we tested, in which the upstream portion of the stream has had the bed elevation increased by about 1.5 to 2 feet. So this might reflect attempts to reconnect the channel to the floodplain. After routing the 5 separate flows through both the original and the altered terrains, we were able to extract a variety of measures from the HEC-RAS results, including maximum inundation surface profiles, which you can see here. This is a cross-section that incorporates one of the Oxbow Wetlands on the left. We also extracted time series of water surface elevations at key cross-sections and time series of two-dimensional depth average velocity. We also were able to extract flow and stage hydrographs at several locations along the reach. And these are just some of the many outputs that were available from the HEC-RAS results. So some of the things that we noticed between our original terrain and the altered terrain, at the upstream boundary of our study reach across all 5 of the flow events, which ranged in size from about 230 to over 1,300 cubic feet per second. At the upstream end across all the events, the average water velocity decreased by about 8%, and water surface decreased by about 2%. At a river station just upstream of a bridge, which marks the end of the region of altered terrain, the altered terrain had an increased velocity of about 7% and a decreased water surface elevation of about 37%. And then at the downstream boundary of the reach, the velocity showed an average increase of about 36%, and water surface elevation decreased about 1% in the altered terrain. But the most interesting results were at the river station incorporating one of the Oxbow Wetlands, where for low flow events, the average water velocity increased about 20%, but for high flow events, the velocity decreased about 11%. So this may reflect the impact of overbank flow slowing the overall velocity when the flow was able to get out of the channel in the high flow events, but having less of an impact for the low flow events. But overall, the results across the along the reach of the study indicate that even a pretty substantial change in the channel terrain resulted in some local changes in flood response overall, but the behavior of the flood wave along the entire reach may not show that much sensitivity to changes within the channel. So some future applications of this work, ideally we would like to compare the pre-restoration and post-restoration terrain. We're still waiting to get some of that terrain data, but it would be very interesting to compare the actual terrain of the channel before the restoration projects to the current terrain and see just how different the flood response is. Using these same techniques, it's possible to simulate the response to various channel alterations and assess the effectiveness of different restoration approaches. And ultimately, we would like to compare the relative impact of channel restoration to watershed scale runoff controls. And this information may hopefully inform future stream restoration and flood mitigation design. I'd like to thank my mentor, Dr. Andy Miller, for his help throughout this project. And if anyone has questions, I'd be happy to take them now.